Okay, so let's start again. So sorry for the delay. We just switched the computer so that it can be. Oops, let me try that. Do you have another USB? Okay. Okay, good. So welcome back. So this part of the lecture is about unsupervised learning. So it was designed to be given by Dr. Zhang, but I will go through it very quickly. So the idea of unsupervised learning is to learn hidden structures of unlabeled data. The hidden structure can be classification or some other organization of the data. So the two properties for this task is that we don't have labeled data. All the data are unlabeled, and we don't have the error. We don't have a way to calculate the error to reward or to penalize the method. So like this, when for supervised learning, we have known labels, so we know what is correct and what is not correct. But for unsupervised, we just have a bunch of data. We want to identify underlying structures in the data, which may be of this classification or maybe other type. So there are three major types of unsupervised learning tasks. One is density estimation is a basic task for unsupervised learning because the density distribution is a basic structure of the data. And when there are classes in the data, so finding the classes is called cluster analysis. And maybe there are some other high order hidden structure that is a latent variable analysis. So first, let's look at density estimation. It's quite standard, so I will go through it very quickly. The basic idea is that we want to find the probability distribution of the data. So there are many applications. Once we have the density, we can do the Bayesian classification based on the posterior density, and also we can infer relationship between features and infer properties of behind the data of the sample population. And the simplest method for density estimation is that we can do a histogram, which is a kind of non-parametric estimation. We don't have a parametric model for the density. We just get the histogram. So of course, this histogram will not be smooth unless you have a lot of data. So a smooth version of the non-parametric estimation is the so-called Parzen window estimation. In statistics, you may call it a kernel estimation. So the idea is that for each training sample, we get a kernel, and we sum up all the kernels and normalize them to get the density estimation. So those are the non-parametric estimation. That is when we don't know anything about the data, we just figure out the density estimation. For some scenario, we may know or we may guess the density function, the form of the density function. Like if we have we want to estimate the distribution of the height of the people, we can assume that it is a Gaussian distribution. So in that scenario, the task of density estimation is a parametric estimation to estimate the parameters of a density function of known form. And idea for doing this estimation, there are two major ideas. One is the so-called maximum likelihood estimation. That is, we use this joint probability of all the data. For each x is a sample. If we know the parameter, then we can calculate the joint probability. But if we don't know the parameter, here the parameter is a variable, the data are known, then this joint density function is a likelihood function of the parameter. We maximize this likelihood. We find the parameter by maximizing the likelihood. And the other idea of doing this estimation is the Bayesian approach. That is the maximum a posterior approach. That is, we want to maximize the posterior probability, the distribution of the parameter. We take parameter itself as a statistical variable, and we estimate the maximum posterior probability of the parameter given the training sample. And this can be decomposed to, using the Bayesian theory, decompose this to this, the probability of the sample given the parameter. And we do this expectation. So what we are assuming here is that the x is a univariable. When we have multiple variables, the simplest case is that we assume that the multiple variables, they are independent between each other. So the probability will be just the product of all the probability of each individual variable. And when we apply this on the classification task, the C is the class label, then we get the naive Bayes method, which is just to calculate the probability of the label given the sample. Actually, this can be presented in a graph. That is, the class label. Class label is one variable we want to estimate to predict, and we have the sample, the features of a sample. The multiple features, they are independent. We can think that for class 1, there is a model in class 1 for the distribution, for the density of each feature in class 1. So the density of the feature in class 1 depends on the class. In class 2, so the density of the feature depends on the class label. So this can be represented in this graph. And this leads to the more complicated graph of Bayesian network, which is a graphic presentation of the dependence between multiple variables. Suppose we have 5 variables, and x2 and x3 depends on, so x2, x3, x4, x5 depends on x1, and x4 depends on x2 and x1, so on and so forth. This dependency can be written as in this form, and it can be conveniently represented in this graph. And in the general form is that the joint probability of all the variables is the product of all the probability of given the parent nodes. So this is called the Bayesian network. And the learning in this Bayesian network is that we want to estimate the probability at each node. If the node is discrete, we estimate the conditional distribution table. If the node, the variable is continuous, typically we assume it is a continuous Gaussian or some other known function. And similar to the univariable case, we also have 2 approaches to do the estimation. One is the so-called maximum likelihood approach, and the other is the so-called maximum posterior approach. In the maximum likelihood approach, we have the EM algorithm. For the MAP, we have the Bayesian algorithm. So these are about the parameter learning. And a more challenging task is the structure learning. That is, for parameter learning, we assume we know this structure of dependence between the variables. But how can we know that? So this is a more challenging task. Actually, people really don't have a very good solution here. So usually, for most of the successful applications, we just by human expert specify the structure by knowledge, by domain knowledge. And but there have been some study about how to optimize the structure using some learning task. And after you have got the structure and also learn the parameters, there is another task that is to do the inference, which is to calculate the probability of a particular node in this graph, given some other observed, say, given the values of on these two nodes, what is the probability of a particular other node? So the Bayesian network is that we know the dependence. We use the graph to present the dependence. When we don't know the dependence, but we know what is independent, so this gets the more general form of the so-called Markov random field, in which we don't have directions for the edges. Again, each node is a variable here. Each node is a variable, and we know some variables are independent, so they don't have a edge. But for those, there can be a dependency, so we have an edge, but we don't know the direction of the dependency. This is another graphic view. So this gives us a whole family of the so-called probabilistic graphic models. That is, to use this directional or indirectional graph to represent the dependence between random variables. So in this graph, if we use a node to represent a random variable and an edge to represent the conditional dependence, and non-edge means that they are independent. So there are a lot of applications in computer vision, in bioinformatics, in speech recognition, especially in gene regulatory network inference. So that's about the density classification. The density estimation. Another task of unsupervised learning is cluster analysis or clustering, which is we find groups of the samples that are intrinsic to the data. So there are connectivity-based clustering, or centroid-based clustering, and distribution-based clustering. I guess most of us are very familiar with this task. The most famous method may be the hierarchical clustering, so which groups the samples from either bottom up or top down, and we get this dendrogram, the clustering tree. The length of this dendrogram represents the dissimilarity between the branches, and we can cut the dendrogram at a certain level to get several discrete clusters. And a more famous method may be the k-means, or some people call it the c-means clustering, which basically is if we want to look for 3 clusters, we look for 3 means that represent these 3 clusters. And this can be done by minimizing the error of using the means to represent the samples in each cluster. For both hierarchical clustering and the C-means clustering, an important factor is the distance or similarity or dissimilarity measure. So different distance will result in different results. So of course you need to choose your distance according to your domain knowledge, according to your data. For hierarchical clustering, besides the distance between samples, you need to define the distance between clusters. That is called the linkage. Typically you can either use the single linkage, which means the shortest distance between the two clusters as the distance between the two clusters, or the complete linkage, which is use the longest distance between the individual samples of the two clusters as the representation of the two clusters, or you can use the average linkage. And there are several variations of this k-means clustering that we, instead of using k-means, we can use k-median to represent the k-clusters, or k-majoids, or we can use the fuzzy c-means. That somehow is related with the question in the last session. So when we, what we get is not a hard clustering, but rather a probability of a sample belonging to some classes. This is what the fuzzy c-means does. And so all these k-means or c-means, they try to use a single point to represent a class. A generalization is that we can use a density, a mixture model. We can use a Gaussian or other density function as a representation of the class, which gives us the Gaussian mixture model. And all these methods have the limitation that we require to decide the number of clusters before we do the cluster analysis. And also this method prefer clusters of approximately similar size. So if one cluster is super large and the other is very small, then the method may not work well. And there are different methods. There are methods available for trying different cases. For the Gaussian mixture model, is that we assume that the data are a sample of multiple Gaussian distributions, and each Gaussian distribution represents one cluster. So we convert the clustering task to a estimation of this mixture model. And in this mixture model, there are parameters for each cluster, for each Gaussian distribution, and there is a mixture parameter. So the idea is like this. So from the data is a random sample from this mixture of different clusters, different density functions, and there is a random is a parameter that decides which sample, which cluster the sample is from. And this you build this graphic model to kind of forward represent how the sample is the data is sampled from the distribution, and then from the data you can use maximum likelihood or Bayesian method to estimate the parameters. So this is the EM algorithm actually is one way to do the estimation. This picture illustrates how it works. So suppose initially we have a random assignment of each sample to each cluster. Based on this random assignment, we get the two distribution like this, which is very poor. We cannot discriminate the two classes, the two clusters, and this is the discriminant curve. And after some iteration, gradually we can get this density and this density. They are separated from each other, and after more iterations, we get some a perfect separation of the two clusters, we get these two models. And the Bayesian, there is a Bayesian treatment for this, the so-called MC, because I think most of you are from the statistics background, so I assume you know better than me on this. So for the latent variable analysis, is a more general form of unsupervised learning. So which is we want to find the hidden structure as a low dimensional space. So suppose we have a high dimensional data, and we assume or we want to find there are some underlying structure in the data. They are of low dimension. So there are different tasks. If the latent variable are categorical, this is the classes, and the observed data are continuous. This is the case of latent profile analysis. And if the latent variable is continuous and also the observed variable is continuous, we get the factor analysis. For the latent profile analysis, it's just the Gaussian mixed model is an example of this. We think the underlying latent variable is a binary, which is we assume the data are from the mixture of two Gaussian models. Now let's look at the factor analysis that we want to describe the variability among the observed data in terms of some unobserved variables in a lower dimension. The typical method in this is the principal component analysis and singular value decomposition and non-negative metric factorization. They are of the same family. So let's look at the principal component analysis. I guess we are all familiar with this. So the idea is that although we have a high dimensional data, say that suppose 2 is already high. So in this 2 dimension, we think that there may be some underlying structure. In this case, there is a one dominant variable that captures most of the variance in this 2-dimensional space. So this illustrates that although the data is 2-dimensional, the most information is underlying on this one dimension. And this is equivalent to a eigenvalue decomposition. We find the largest. We find the eigenvectors with the largest eigenvalues of the data covariance matrix. And when we have a high dimension data, we will have many eigenvectors. We can get this spectrum of the eigenvalues. The eigenvector with the largest eigenvalue is the first principal component, second, and so on and so forth. We can use the first few principal components to represent most of the variations of the data. And there are many interesting applications of the principal component analysis. One interesting application in artificial intelligence is this so-called eigenphase. So suppose we want to do the face recognition with multiple face training data. We solve the principal component analysis. We get say 8 principal components, and then we can decompose the original input, the image, as a combination of these principal components, which is called eigenphases in this context. So note that these images are not from the same example, so I just use it to illustrate the idea. And using this, when we get a input data, we convert the original image to a very low dimensional feature. Here is the 8 dimension. The weights on this 8 dimension, and we use this weights, we can do the classification using support vector machine or whatever neural network, or some even the linear or the simpler cases. And also from this representation, we can recover the original image in quite reasonable resolution. And but principal component analysis only looks for underlying linear directions that can capture the variance of the data. But sometimes there may be some nonlinear manifold underlying the data. For example, suppose the data is distributed like this. So if we use linear PCA, we only get this direction, which is not a very good capture of the variance. So if we can get this nonlinear direction, it's still one dimension, but it captures more variance in the data. So this is what Kernel PCA done. So the Kernel PCA, the idea is that using the kernel trick in support vector machine, we convert the original space using some nonlinear transform to another space. In that space, we do the linear principal component analysis, and we convert it back to the original space. So these lines are the ISO lines that tells the on this nonlinear dimension, the projection, the equivalent values of these directions are, I mean, the projection values of this direction are equal on this nonlinear direction. So these are some toy data examples of how kernel PCA can reveal underlying nonlinear structures in the data. For this example, the data is distributed like this. This is the linear, the first column is linear PCA. We get the first principal component in this direction, and we get the ISO lines in this direction. And the second principal is this direction. We can see that the linear principal components don't have a very good representation of the data. But if we use a nonlinear, this is the quadratic, using quadratic kernel, we can get this direction, this kind of binary direction. And the second principal component is of this direction, and the third is somehow like this. And this is the third order polynomial, and this is fourth order. And this is using Gaussian kernel. We can say, I think this is interesting. We have 3 clusters of data. The Gaussian kernel will have multiple principal components. And the first kernel kind of discriminates this cluster with this cluster. And the second kernel, it discriminates this cluster with the other 2 clusters. And the third principal component further discriminates some finer scale differences between this within this cluster. And the fourth kind of discriminates some finer structures within this cluster, and so on and so forth. We can say that with this kernel principal component, we can hierarchically find the substructures in the data. There is another neural network for unsupervised learning, that is the so-called competitive learning, the self-organizing map, which was developed by Professor Kohonen of Finland. So I will not go through the details. So basically, they have a array of neurons arranged on this plan. They have computations within a certain neighborhood, and each neuron is connected with all the input variables. And after some self-organizing learning, they get a map of the original input. The high-dimensional input space is represented in this discrete array of neurons. And each neuron here is in speech recognition, each neuron represents a pronunciation. And this has been also applied on microdata to find the time series, the different patterns of time series. And so based on this, we can do some further. So we can treat each neuron as a single cluster, but we can find more high-level clustering between these neurons. So we can use this density to get, for example, to get more. So this more hierarchical clustering of this smaller clusters. So a more sophisticated clustering or unsupervised learning model is the so-called hierarchical modeling of the unsupervised learning, with it models the generalization of clusters using the Dirichlet process, and using the Dirichlet mixture model to describe how each component in your mixture model was generated. So remember that in the Gaussian mixture model, we assume each cluster has its unique a density distribution, and then the Dirichlet mixture model add another layer of to describe how this multiple mixture model was generated using the Dirichlet model. And the famous method is called LDA, or latent Dirichlet allocation. And in the natural language processing, they have the so-called topic model that can identify clusters with undefined numbers. So the advantage of this is we do not need to pre-assume the number of clusters we want. We just learn from the data. But this is too complicated for this short course, so I will skip this. I will provide only one simple application of this. The application is that in the early application, so when we want to do the classification of lymph node metastasis of breast cancer based on the expression data. For some other features in breast cancer, like ER positive, HER2 positive, so on and so forth, we can get very good prediction. But for the lymph node, the prediction using supervised method is poor. But we applied unsupervised learning on the data, and we identified 6 subgroups, 6 clusters of the data. And within each cluster, we built this logistic regression model. And within each cluster, we can have a better prediction accuracy. And also, this clustering method shows some hints about the pathways in the lymph node metastasis. So I went through this part very quickly. So any questions for this part? So now let's come to the deep learning part. So where is my mouse?